Howdy folks, this is the ZN squared statistic. It's something that I and many others use commonly to do timing work with X-ray and other high energy data. But more particularly, I've only been using it with one harmonic, or n equals 1, effectively fixing k equal to 1 and eliminating this entire first sum. But in this video today, what I want to explore is what happens when we introduce more than one harmonic with this Zn squared statistic. Alright folks, so yes, the Zn squared statistic, that's the topic of discussion today, more particularly what happens when we use more than one harmonic with this statistic. If you're unfamiliar with what the Zn squared statistic is, don't worry, I will do a brief rundown of what this statistic is to let those of you that don't know what it is, or to give those of you who do know what it is a bit of a refresher. I have introduced this and talked about it in two previous videos, which you can check out, but do note that I did leave a typo in both of those videos where I forgot about these outer brackets, so it looked like this first sum right here was only being applied to the cosine term. It's definitely not. It's definitely being applied to both the sine and cosine term. So I left a pinned comment on those videos, but nevertheless, it doesn't really matter too much. Like I said from the beginning, little n in this Zn squared statistic on the top is the number of harmonics that we are using. Big N is the total number of photon arrival times in a given observing interval or exposure interval, depending on whatever you want to call it. And then Ti and T naught are photon arrival times. T naught is the first photon arrival time of an observing interval, and Ti is each subsequent photon arrival time. Then, using this phase model on the bottom, we can compute a collection of phase models for all of those arrival times, using different values for nu and then subsequent derivatives if we want those derivatives. For the case of this video, we're just going to be looking at the 0th order model right here, so we're not going to be using any derivatives, but that's just going to be a test frequency. And so what you can do is you can take a collection of phase models and use a wide domain of test frequencies, and you can basically just go ahead and then take that and plug all of that into this Zn squared statistic up on top, and it's going to do kind of like a Fourier transform. And this is the type of result that we might expect to get. We're actually going to take a look at this result and multiple others like it before, but we can just basically then take our test frequencies and stick them in a power density like you can see right here, and the real power of this Zn squared statistic, though, is that we get, instead of some arbitrary gain or amplitude like you might get with the Fourier transform, you get a statistical interpretation of how well a given frequency fits to the photon arrival times of the data set. And this is significant because the Zn squared statistic value is statistically equivalent to a chi-squared with 2n degrees of freedom. Again, this little n value being the number of harmonics that we are using. And to really kind of better understand where these harmonics come from, not just the harmonics, but particularly the degrees of freedom come from, you're dealing with one harmonic in the cosine term, or the cosine squared term, and another degree of freedom in the sum of sines squared term. And so for each harmonic that you are using, you're doing additional sums from this outer sum right here on the far left. And so you're going to get 1 degree of freedom from the sum of cosine squared term, and another degree of freedom from the sum of sine squared term, and for each harmonic you have to do an additional sum, so that's where we get the 2n from. So that is our 2n degrees of freedom with this. Now, in order for a result to be considered a coherent frequency, or coherent oscillation frequency for that matter, we set a threshold of 5 sigma. Now, different people might have different criteria, but for me, I look at 4 or 5 sigma statistical confidence, or ppf, in the magnitude of that Zn squared value, which, as you can see right here, we have the total number of harmonics that we're introducing, the corresponding degrees of freedom. Those degrees of freedom are just 2 times the total number of harmonics, and this is the corresponding threshold that we need to exceed for 5 sigma statistical confidence, or again ppf, in the actual result. And so if we go back to this example that I showed to you from before, from this NICER observation of the Crab Pulsar, this is NICER OBS-ID 301.301.0105, taken in 2020. It's one of my favorite test data sets to go through. You can see that we definitely have a very, very strong and clear coherent result right here. A nice, clean, Gaussian-looking shape. Full width half max can be our error bars, and this is the type of result that we might expect to get. And with this being Z1 squared, you can see that we are well above the 30.2 threshold for this to be considered 5 sigma. That's particularly why so many people love to use the Crab for testing and calibration and whatnot. That's why I love using particularly this test data set and multiple others like that with the Crab to do calibration and testing and whatnot, because it's really easy to get good, clean timing results out of Crab data. But the question is what happens when we introduce more than one harmonic, or compute Z2 squared, Z3 squared, so on and so forth. So what I've done here is I have gone ahead and used my, for the moment, closed source code called Time Wrangler, which is just an implementation of the Zn squared statistic, and I have gone through and I have computed or processed the same NICER data set for the Crab Pulsar between Z1 and Z20 to see what happens with those results. Let's take a look at them right now. And so this is the result that I showed you from before. I just have this table added on the side. You can see we get a nice measurement right here at 29.60859 hertz. The error bars, again, are full width half max at about 8 microhertz. And we get that Z1 squared value of 758 and some change. It's a nice, very, very clear, coherent result, as you can see. But what happens when we go to Z2 squared? Well, would you look at that? Our Z2 squared value jumps significantly, and our error bars nearly halve. Let's take a look at that again. You'll notice that we see significant improvements in the results with Z2 squared rather than Z1 squared. As we bump things up to Z3, again, you see significant improvement. Z4, significant improvement. Those error bars continue to shrink. And as we continue to go up, you continue to see those error bars shrink. The frequency does change ever so slightly, but the Zn squared value also does increase. If we go back to this table right here, you can see that we are well above the thresholds of what is considered 5 sigma. That's, again, why we are using the Crab, because we can reliably get really good results that, surpass this threshold. Let me just show you exactly what happens as we go from Z1 to Z20. We'll stop at Z20 and we'll talk about, just how good of improvement we actually end up seeing. Okay, so as you can see, we are dealing with significant improvement to our error bars. Our result is not so Gaussian-like anymore. I mean, it's still, you could kind of approximate it to be a Gaussian, but it's not quite so Gaussian. But definitely between, let's say, Z15 and Z20, we really start to get diminishing returns. But nevertheless, this is something where we could just keep adding more and more harmonics, in theory, based off of what I'm seeing right here, and we could get better error bars along the way. But this brings up an interesting point. What happens to the natural harmonics that we would expect to find in this domain as well? Because I'm just searching on a very narrow domain right here. I'm only searching between 29.5 and 30 hertz here, because that's where we would expect to find the spin frequency of the Crab Pulsar. What about subsequent natural harmonics that we would expect to find in this domain? So I took the same dataset, NICER dataset 301.301.105 from the Crab Pulsar, and I looked at exactly 2 times the value that we were finding. Actually, it was more so between 59 and 60 hertz. And let's take a look at the results that we see from that. For the first harmonic of that same data set for the Crab Pulsar, the Z1 squared value that we end up getting is 1,853 with some nice error bars, and this is at, pretty much perfectly 2 times the frequency that we measured before. It's never going to be exactly perfect, but within error bars. This is the harmonic, but notice a particular issue here. This is z1 squared, and our z1 squared value is 1,853. Going back to the expected actual spin frequency of the Crab pulsar, not the first harmonic, you can see that we only have a magnitude here with the z1 squared of 758. That's problematic because the magnitude of this first harmonic signal dominates above the actual expected spin frequency for the Crab pulsar that numerous others have found and have tested against. And this is problematic because the methodology that I am using to mine through this data and look for coherent oscillations or evidence of coherent oscillations relies on picking out the dominating spin frequency and assuming that to be the spin frequency of the pulsar. Now, I'm doing stuff with phase resolved light curves and whatnot. We're not going to get into that, but this is problematic. Let's see if the problem persists, though, once we jump up to more and more harmonics. Here we have z2 squared. We see significant improvement. We went from about 1,800 now to over 2,000. Again, the error bars did shrink ever so slightly. This is still a strong coherent result, but let's compare it to the actual spin frequency of the actually expected spin frequency for the Crab pulsar at z2 squared. Here you can see we have, again, better error bars from what we got originally for this signal, but now we have a magnitude, or z2 squared value, of 2,609. That is larger than what we got before. So now this first harmonic is not the dominating frequency any longer. And if we continue, we can see that this continues to grow, but once we reach z5 squared, which is where I decided to stop with this, we get a z5 squared value of 2,800, whereas on the same data set, for the expected frequency related to the spin frequency of the Crab pulsar, we get a z5 squared value of 5,533, which means that now this frequency is the dominating frequency in the domain, but don't just take my word for it. I've gone ahead and I've processed the same data set between 29.5 and 150 hertz at 10 microhertz resolution, and this is what we end up seeing for one harmonic. You can see that first harmonic is definitely the dominating frequency. It has the largest magnitude right here for z1 squared, and not only that, but the second harmonic and also the fourth harmonic are greater than the actual expected spin frequency, or the actual expected frequency related to the spin frequency of the Crab pulsar here on the far left. I don't know what's going on with this third harmonic, of why it is so weak, but that's interesting, and you'll kind of see that persist here as we go through. But watch what happens when we introduce a second harmonic. With two harmonics, look at what happens. Our expected frequency related to the spin frequency of the Crab pulsar dominates above all the rest, but notice something else too that's particularly interesting. Count the total number of spikes that we have in this figure. I'm counting 5 right here, but we know that 4 of those are harmonics. At Z2, now count them. We have 1, 2, 3, 4, 5, 6, 7, 8. That 7th one is kind of hiding away there. But we've now doubled the total number of spikes, if that's what you want to call them, that we have here in this test domain. That's what I mean when I say we're introducing an extra harmonic right here. Take this out to Z3 squared, and you can see that our actual the expected frequency for the Crab pulsar now dominates above the rest, even more so than before, and we get many, many more spikes. If we go to Z4, a similar thing, we're still continuing to dominate even more than we were before. And Z5, we are almost twice as dominant as that first harmonic, and again, we get more spikes. Some of them are probably so weak at this point that they're, not visible in the frame right now. But as you can clearly see, introducing more harmonics not only improves the error bars of our results, but it makes the expected, or not the expected, but the actual frequency related to the spin frequency of the pulsar begin to dominate. But as many of you may know, we can't just test one data set from one mission, so I picked out a dataset from an XTE mission and ran similar tests. This is XTE OBSETI 90802-020600, taken in 2004 of the Crab Pulsar BO531 plus 21. And this is the broader Z1 squared result that we end up seeing. This time, interestingly enough, it's the second harmonic that dominates above the actual expected frequency related to the spin frequency of the Crab Pulsar. You can see we have very, very strong results on with very, very strong magnitudes right here. And so, these are very, very strong nonetheless. Also notice that, with the Gaussian fit that's going on here, my code on the back end is designed to fit a Gaussian to the most dominant frequency in the domain, and that is, of course, in this case, that second harmonic. The third harmonic there, for whatever reason, is still very, very weak. I'm going to have to look up some literature for that. But what you'll see here is that once we introduce a second harmonic, now all of a sudden the expected frequency related to the spin frequency of the Crab Pulsar is now the most dominant. It's definitely the most dominant. We introduce more spikes like we saw from before, and if we go to Z3, look at how dominant this becomes. We have a Z3 squared value of greater than 120,000. Folks, this is why you choose to do calibration and testing with the Crab, because you're going to get really nice, clean results and coherent, certainly extraordinarily coherent results like this. But that comes at the cost of processing time, of course. That's why I didn't go past Z3 squared. Instead, I decided to look at more XTE data, this time for a different source that I know also provides very clear, coherent results. This dataset is XTE OBSETI 90419010600, taken in 2004 of the Hercules X1 source. I should have mentioned before that this is PCA data taken with XTE, and you can see a very clear, coherent result at the expected frequency related to the spin frequency of the Hercules X1 pulsar at roughly about 0.8 hertz. With this test, I am going between half a hertz all the way up to 8 hertz, and you can see we definitely get some harmonics in there. But with Z1 squared in this case, what's particularly interesting is that the actual frequency of Hercules X1 is already the most dominant one. So do we even really need to go and use more harmonics? Well, when we do that, we see the same thing that we saw before. Some more spikes. They're very, they're very, very weak comparatively. But what you can see is that the magnitude of this result does increase substantially, and that's going to make our error bars much, much better. Here I picked another data set with Hercules X1 just because there's not really any nicer data for this. I actually don't think there's any nicer data for this. But this is XTE OBSETI 20050011000, taken in 1997. You can see this is a much, much weaker result with Z1 squared, but again, just with Z1 squared, that 0.8 hertz signal is the most dominant. So we don't even really need to go past Z1 squared. We would expect to see improvements again in that magnitude and therefore better error bars, but we don't need to go past this really. And so naturally I had to test this out with one other source. I went back to some nicer data and looked at some nicer data for a very well studied source with the nicer mission. That source being Pulsar J0030, which I am going to propose a unique name for and call it the nicer Pulsar. Yes, I'm going to call it the nicer Pulsar throughout the rest of this video. I reran all the same tests for Pulsar J0030, or the nicer Pulsar. Yes, like I said, I'm going to call it the nicer Pulsar. I hope it catches on. That's my proposed name for it. Anyways, this is the first result that we ended up getting. We expect the spin frequency to be somewhere around 205.53 hertz. But as you can see, we are just barely meeting the threshold of 5 sigma confidence in this result using Z1 squared. However, when we jump to Z2, all of a sudden we see nearly, or more than, well, not quite more than, but nearly 6 times improvement in the Z2 squared result from Z1 squared. Our error bars actually do get a little bit worse because now the fitting is doing some weird stuff because there's too much noise in here. And so the way that I have this programmed up actually is that the error bars, if there's too much noise, actually get computed from the Gaussian fit. But there is significant improvement here. Going up to Z3 squared, though, we only see marginal improvement. And so, for a sparser data set, which this source is definitely much sparser, we're dealing with nearly 2 orders of magnitude less photon arrival times, I believe. I'm not entirely sure about that, but I know it's at least an order of magnitude less arrival times. But anyways, you can see we see a natural stopping point between Z2 and Z3. We could go to Z4, but again, there's such little significance in the level of improvement that we might as well stop at some point. And so this tells me that with certain data sets, there is a natural stopping point. It's not just all going to be like the crab, where it's just going to keep on getting better and better as we start introducing more and more and more harmonics. There can be a natural stopping point at a certain point. And we see the same thing going all the way up to Z5 squared. Well, here for the first harmonic for the NICER Pulsar, I should have mentioned that this is NICER OBS ID 10600-20106, taken in 2017. This is a really early NICER observation, by the way. I love dipping into these earlier observations that I worked with a lot in the past. But here, Z1 squared value is 152 for this first harmonic, at exactly 2 times the frequency of what we would expect to be the the frequency related to the spin frequency of the pulsar. You know, remember, this is a very, very weak result. This is barely breaking that 5 sigma threshold. It's not the most dominant frequency. And you can see with Z2, we only see marginal improvements to 155 at Z2. Going back to Z2 for the actual expected frequency of the NICER pulsar, we're at 184, so we're already surpassing it. This is now the dominating frequency. And so going back to the crab here, what are the takeaways from this exploration of introducing more harmonics or using more harmonics with the ZN squared statistic in the context of me wanting to mine up as many high-quality measurements of oscillations related to pulsar spin frequency to catalog and document the evolution of the rotational dynamics of different pulsars in the X-ray band, as I've been doing, and as you can see on my archive, where I only used Z1 squared. Well, the first takeaway is that measurement attempts with more than one harmonic must be used. So using Z1 squared is a good starting point to see if there's something coherent in the frame, but I need to use more than one harmonic, at the very least, to provide improvement to the existing results. It's going to increase the statistical evidence for oscillations at that frequency, and it's going to improve the full width half-max error bars. And at the very least, the full width half-max error bars, you should try to maximize and get as best of error as you possibly can get out of these. Once you reach the point of diminishing returns, obviously, that's a good stopping point, but we want to try to improve our error as best as possible. Secondly, we want to use more than one harmonic to allow for the oscillation related to the actual pulsar's rotation, or the actual pulsar spin frequency, to dominate in the domain. We don't want the harmonics to dominate based off of the methodology. The methodology that I'm using is that the most dominant, or the frequency with the most dominant Zn squared value or magnitude should dominate above all the rest, because it's the frequency related to the pulsar spin, which is like the main thing we're interested in going after. Like I said, obviously, I am doing additional work looking at pulse profiles and whatnot, but if you're just going off of frequency alone and making the assumption that the most dominant frequency in the domain is the one related to the spin frequency, that would be a pretty good educated guess, in my opinion. That brings us to the second takeaway, though. A dominating signal test must be done to verify that the frequency that we believe is the frequency related to a pulsar's rotation is actually the most dominant one in the timing domain. And so basically, we're just going to take that frequency, like we saw here for the crab, and we're just going to compare the different Zn squared values once we reach a good Zn squared stopping point, and compare it to each harmonic, possibly even 5 harmonics, who knows, and just ensure that it is the most dominant frequency in the domain. We don't have to test or compute everything else here in the middle unless we're expecting some other signal coming from another source or some other type of noise to get in the way. If the signal still dominates compared to all of those other harmonics, then it's a pretty good chance that it is the frequency that we can assume to be related to the frequency of the pulsar. Obviously, all of the results that I have put up on the archive, they're not wrong results. They're wrong in the context of the methodology, where they are not the largest or most dominating signals in the domain, because I'm just testing around where I would expect to find the frequency. But I'm definitely going to have to go through and remine all of this stuff up using more and more harmonics to improve the error bars, and also make sure that they're the dominant signals in there. Additionally, I should note that if you do go and look on the archive, I found an extra factor of 2 in my code somewhere, so the error bars that are displayed there are actually not full width half max error bars, they're half width half max, so just multiply all those by 2, but eventually new results will get posted up there that are in fact correct and are the actual full width half max error bars. That said, though, if you made it this far, thank you very, very much for watching. Hopefully you found this informative or entertaining or educational, useful, whatever. If you have any questions, comments, or concerns, or even if you just want to nerd out about this, don't hesitate to reach out. Don't hesitate to leave a comment and let me know what's up. Thank you all again very, very much for watching, and I'll hope to see you all again next time, where we'll talk more about math or pulsars or astronomy or who knows what.